This example deals with what we need to do when we're raising something to a power in an experiment and we need to deal with the uncertainties or the errors in that measurement. And I've got a note at the top. It says when raising to a power, we need to multiply the power value by the percentage uncertainty. So I have a value, 42.0 plus or minus 0.05. That's my uncertainty, my absolute uncertainty in that measurement. And I need to take the square root of that. So one thing I need to do right off the bat is calculate the value. So I'm going to take the square root of 42.0. My calculator kicks out a big number. It says 6.480740698. But I know by looking at the value 42.0 that I need to report my answer with 3 significant figures. So I'm going to look at my first 3 digits that I have there, 6.48. Then I look at the value directly behind the 8. It's a 0, so it's not 5 or above, so I do not need to round up. So I leave it just at 6.48. Next, I need to calculate the error. Generally, I just need the percentage error, which is 100 times the error from my absolute value, divided by my value that I get in the experiment. So 0.05 divided by 42.0 times 100. However, now, since I'm taking the square root of the value, I need to multiply the power value by my percentage uncertainty. Well, my power value, if I'm doing a square root, is actually raising it to the 1/2. So that's why I have a 1/2 out front. I'm multiplying my percentage uncertainty by 1/2. So I do my calculations. I'm going to have 1/2 times 0.1190476619, and I get 0.05952 and I need to figure out how many significant figures I need. So I look at my initial values and I think about my sig fig rules when I'm doing multiplication or division. I look at the total number of significant figures in each value and I choose the one that is lowest and I use that number of sig figs in my final answer. So 0.05 has 1 significant figure and 42.0 has 3 significant figures. 1 is less than 3, so I'm going to have 1 significant figure in my final answer. So the 0.0, neither of those numbers are significant. The 5 is, that 5 that's in the 100th spot is significant to me. So I need to look at the value that's directly behind the 5 to see if I need to round up or not. And it is a 9, so I do have to round up. So my percentage error is going to be 0.06. And I can report my answer as my value plus or minus my percentage error, so 6.48 plus or minus 0.06%. Now, the problem didn't call for it. However, it's good practice for us to also calculate the absolute uncertainty, which I need my percentage uncertainty to determine for these. And I'm going to do my value times my percentage uncertainty that I just calculated divided by 100. And I'm going to use my pre-rounded values because if I use my rounded values, I might get round-off errors, especially if I do more and more calculations. I don't want round-off errors, so I'm going to go back to those values that the calculator gave me originally. So I calculated the value to be 6.480740698. And I calculated my error to be 0.05952381, and then I'm going to divide that by 100. And I get a value of 0.003857584. Now to figure out the correct number of sig figs, I go back to my initial numbers. I had a 42.0 and a 0.05. And since I'm doing multiplication in these problems, I need to look at the lowest number of sig figs of my initial starting values. I had 3 for 42.0, 1 for 0.05. I choose the 1 because that's the lowest of the values, and I'm going to report my final answer with 1 sig fig. So the 0.00, the leading zeros, are not significant, so I do not count those in my 1 significant figure that I have. What I do start counting at is where the 3 is in the thousandth spot. And I look at the value behind the 3 and I see that it is 5 or above. It's an 8. So I'm going to need to round up. So my absolute uncertainty for this value is 0.004. And I can report my final answer, 6.48 plus or minus 0.004.